Welcome to our first lecture on plastic analysis. It is presumed that elastic analysis is fairly very well known to the students. All the same, we will have a brief revision of elastic analysis in the beginning. So this is the famous stress strain curve for a mild steel Fe250 specimen as you load the specimen axially on universal testing machine. Let's see the saline points of this curve. This is where the specimen has its natural length, no stress, no strain, and then you start loading the specimen. Initially, you come to the linear elasticity region, that is, you are observing stress is proportional to strain, and we come to point A, which is proportionality limit. There onwards, the curve is not linear, it is non-linear. However, the material is still having elastic properties, and then you come to the point B, which is the elastic limit, which is where we observe that the fibers begin to yield. There onwards, B to C region, this is plastic region, where the yielding continues. There is no more resistance offered by the material, so stress is remaining more or less constant, and we are observing that strain is increasing continuously. At C point, a strange phenomenon called strain hardening takes place, where suddenly the material starts to exhibit more and more resistance, more and more stress to the loading, opposition to the loading, and then at D point, necking takes place. D is the ultimate stress, that is the maximum stress that can be borne by the material, and necking takes place, and there onwards continuously the resistance keeps on falling, and at E point the material fractures, the specimen break. And about E dash point or E prime point, we can say that actually CDE is the theoretical curve by considering original cross section, but we are aware of the Poisson's effect that cross section starts to reduce as the material elongates. So practically, actually, because of lesser and lesser cross sectional area, the stress goes on increasing like this. So this is the practical curve, and this is rather theoretical curve with original cross section. Analysis of structures which is based on elastic properties alone is called as elastic analysis. So what we just now discussed, up to B point, material is having all the elastic properties, and there onwards we are seeing plastic zone. So if we are analyzing the material or designing the material taking into consideration only limit up to A or B, then we are saying that it is elastic analysis or it is elastic design. What is happening in elastic design? Working stress is restricted to a fraction of yield stress by applying factor of safety. So conventionally what we have been doing, since research facilities were not available in the earlier times, we used to consider yield stress as the limit of loading or limit of material strength, and then to this yield stress sigma y or sigma permissible, we were dividing by some suitable factor of safety, and working stresses, in the working condition we were limiting our stresses only to this fraction of yield stress. Because of that, what happens? Our section is quite large. The design is actually uneconomical. Yielding of outermost fiber does not imply complete failure. So these are the limitations of our elastic analysis. In bending, you will observe outermost fibers to begin yielding first. But that doesn't mean that the material or the section or the member has totally failed. Factor of safety does not represent realistic limiting strength. So when you limit your working stress to a fraction of yield stress, actually a lot of reserved strength that you are observing in the stress strain curve. All this stress or all this strength you are simply not utilizing. You are simply considering that material has failed, which is not the reality. Elastic analysis does not consider reserved strength of material beyond elastic limit, that is what we discussed just now, and it does not predict what will happen if the stresses exceed elastic limit. So fine, you have designed the section using elastic analysis, but whenever there is overloading, like there is tsunami or there is earthquake, then what will happen once the section yields? Then how the section will behave, and accordingly what provisions you should make in your design. All this you have not simply considered in your elastic analysis. So these are all limitations of elastic analysis. And now we are gradually coming to the plastic analysis, where we are not just restricting ourselves to the yield stress, but we are also thinking of what happens beyond yield stress. So you are observing here is a curve which is idealized elastoplastic curve, also called as Prandtl diagram, where you are seeing that there are only two distinct portions in the curve. The first one is of course of the linear elasticity, that is O to A, and there onwards we are just assuming horizontal behavior or stress remaining completely constant, which is yield stress. Two distinct portions, linear stress strain part and then yield plateau. Elastic properties are assumed to hold up to point A, and beyond point A, the deformation may become indeterminately large under the same stress. So stress remains constant and the elongation or the deformation goes on occurring indeterminately. These are our assumptions of the plastic theory or plastic analysis. Effect of strain hardening. In the earlier stress strain curve at point C, we had seen that suddenly the stress started to grow up to the ultimate stress beyond which necking occurs. So in our idealized elastoplastic curve, we are simply ignoring that effect of strain hardening. That means we are not going up to that limit actually. We are just imagining linear elastic zone followed by plastic zone. Structural analysis, which is based upon this idealized elastoplastic curve or Prandtl diagram, is called as plastic analysis. Okay, so let us go more in depth into the plastic analysis, and what we are seeing here is this is a simply supported beam which is, let us say, loaded by uniformly distributed load of intensity small w, and this is the bending moment diagram which is parabolic in nature, we are aware. And then what am I doing? I imagine that this w continuously goes on increasing. So as w goes on increasing, the bending moment at the center, mid-span bending moment, will also continuously go on increasing. Now what is the effect of this continuously increasing bending moment on the mid section of this simply supported beam that we are trying to see? And all this will help us develop our theories, our concepts, our derivations for plastic analysis. So we are assuming that it's a simple rectangular B by H section of the beam, and under working conditions, that means we are yet to reach the bending moment which develops yielding in the outermost fibers. Under moderate loading or moderate bending moment, this is the bending stress diagram. Sagging bending moment, so we are assuming compression at the top and tension at the bottom, and the stress in the outermost fiber is less than the yield stress. This is what we are writing here. Stage A, loading is within elastic region, and for all fibers stress is proportional to strain. That's why you are observing a linear distribution here, and the stress, outermost stress, is less than yield stress. Now I have increased the load, I have increased the bending moment, and what has happened? The outermost fiber has reached yield stress. Same is the case at the bottom, outermost fiber also. It has reached maximum tensile stress, this has reached maximum compressive stress. And obviously, if you remember that elastoplastic curve, this is the maximum stress that can be taken or offered by the fiber. So this fiber, it may elongate further. There may be strain in this fiber, but it will not offer any larger resistance. It will not offer any more stress. What we are writing, our observations for stage B, extreme fiber has reached yield stress, that is sigma yield. Inner fibers, this is very important, are in elastic range. So for all these fibers, the stress is still less than sigma y, and the color coding that I am using here is the blue soothing color is suggesting that the stresses are within elastic limit, and the red colored, which is a warning sign, is suggesting that the elastic limit has been reached, the yield stress state has been reached. This calculation is known to us from mechanics of materials or strength of materials subject. The elastic moment of resistance ME is equal to sigma y, that is yield stress, into I, which is second moment of area, upon Y max, distance of the outermost fiber from the neutral axis. Neutral axis is where there is no tension, no compression. The fiber is, or the layer is, having its original length, and this I by Y max we define as Z. Here deliberately now I am calling it ZE, E indicating elastic. So I am getting moment of resistance ME is equal to yield stress multiplied by elastic section modulus ZE. Well, I have further increased the load. The bending moment is further increased, and now we are entering elastoplastic zone or plastic zone. So what is happening, as discussed earlier, the outermost fiber could not offer any more stress, so the more resistance is now offered by inner fibers. So just see what is happening in the section, which is very interesting. The outermost fiber has stopped offering more resistance, but since there is more load, since there is more bending moment, the inner fiber has now yielded. It has offered more resistance compared to the earlier stage of loading. You can see that in stage B, the stress in that fiber was smaller than yield stress. Now it has become equal to yield stress. So what our observations are for stage C, extreme fiber cannot be stressed further. Inner fibers gradually take up more stresses and start to yield. I am going even further now. The load is even further increased, and we are observing that a large number of fibers have undergone yielding. More and more fibers are taking more and more stress. Their stress have become sigma y, that is yield stress, and now clearly the section is divided into two zones. This part is plastic zone, where all these fibers have undergone yielding. This part, a small section of the cross section or a small portion of the cross section is now remaining elastic, that is sigma is less than sigma y. So we are calling it as elastic core, and these two are plastic zones. With increasing load, the yield has spread further deeper in the section. Partial plastic bending of the beam. So partially the section is in plastic state, partially it is in elastic state. What we are observing here is the bending moment has reached such a high value that all the fibers of the section have undergone yielding. Each fiber has developed sigma y. With more load, yield has spread throughout the section. This is called limiting equilibrium condition between loads and stress resultants. Why am I calling it limiting equilibrium? Because this is the maximum resistance that the section can offer. All the fibers, the entire material of the section has reached yield stress. It cannot offer any further stress. And you remember in that Prandtl diagram or elastoplastic idealized curve, that strain hardening effect we are ignoring. So this is the maximum stress that the section fibers can offer, the maximum resistance they can offer. So we are saying that this is the limiting equilibrium between applied loads and resistance or stress resultant. The layer which is unstressed is called plastic neutral axis. Again, theoretically, we are assuming that centrally there is a layer which is not stressed, not strained. From stage A up to stage E, you can theoretically consider such a layer which is called PNA, plastic neutral axis. A so-called plastic hinge is formed. So what is a plastic hinge? When all the fibers of a section have reached yield stress level, we call the section to be a plastic hinge. Any further increase in load will cause the beam to deform indefinitely. Just now we discussed that a limiting equilibrium has been reached between the load and the stress resultant. So if you further increase the load, the section will not be able to offer the resistance and there will be an indefinite deformation or bending in the beam. The load that causes the structure to collapse, or I will slightly modify and say the load that causes the structure to be in the state of about to collapse is called ultimate load or limiting load. So in plastic analysis, our focus for a beam or for a frame or for any structure is to calculate essentially this ultimate load or limiting load. This is most interesting, plastic moment of resistance. Clearly, the moment of resistance offered by section in fully plastic state is the couple moment formed by stress resulted C and T. You are observing that all these fibers are in compression, all these fibers have developed yield stress, all these fibers are in tension, all these have developed tensile yield stress. So the stress resultant of these fibers is the compressive force here, and the stress resultant of these fibers is the tensile force here. Clearly C and T are forming a couple. From the rectangular shape, you can imagine that the centroid of this rectangle, which is a cross section of the diagonals, is going to be where the compressive force is acting. Similarly, the centroid here is where the tensile stress resultant is acting. That is why if this is h by 2 and h by 2, even this distance will be h by 2, remaining distances will be h by 4 and h by 4, and T and C are forming a couple. Compressive force and tensile force will be equal and opposite, obviously, because the beam is not being axially loaded at all, it is only loaded transversely. How to calculate this compression or tension is obvious. Sigma y is the stress multiplied by the cross-sectional area over which it is acting. In the diagram, I have deliberately highlighted that area. This stress is acting over h by 2 multiplied by b area. So my C, compressive force or tensile force for that matter, is sigma y multiplied by h by 2 multiplied by b. Then how do I calculate plastic moment of resistance, that is moment of resistance at the stage where load is so high that the entire section has undergone yielding and a plastic hinge has been formed. So we calculate it as MP, we call it plastic moment of resistance MP is equal to C or T, one and the same, multiplied by h by 2. So this is our basic engineering mechanics. How do we find couple moment? Force multiplied by distance separating the two forces forming the couple. So I am writing C multiplied by h by 2. C I have already expressed as sigma y into h by 2 into B in my earlier step, into this h by 2 as it is. Now this highlighted portion h by 2 into B into h by 2 I am calling as ZP, called as plastic section modulus. So here we are establishing another extremely important equation. Plastic moment of resistance is equal to sigma y yield stress multiplied by plastic section modulus. ZP is called plastic section modulus. That is what we discussed just now. And we have already discussed that this neutral axis is called plastic neutral axis. More about this plastic section modulus. What is it exactly? Let us try to understand its physical existence or physical significance. So I have repeated the earlier expression. ZP is h by 2 into B into h by 2. If we go back just one slide, you will see that the same part was highlighted and the same part was called as ZP. So the same thing I am writing in my next slide. I am saying ZP is equal to h by 2 into B into h by 2. This may be rearranged and written as B into h by 2 in one area multiplied by h by 2. There is a reason for this particular grouping of terms. Just observe this h by 2. I am splitting as h by 4 and h by 4. So the same expression B into h by 2 into h by 2 I am writing as B into h by 2 into h by 4 plus B into h by 2 into h by 4. You may get a fairly good idea why am I doing like this from the diagram. You are observing that B into h by 2 is this half the area which is under compression, for that matter remaining half area which is under tension. So these quantities in brackets, they are indicating area in compression or area in tension. And what could be h by 4? So you can clearly see that if this distance is h by 2, this half the distance is going to be h by 4. That is this centroid up to the plastic neutral axis and this centroid up to again the plastic neutral axis. This distance is going to be h by 4, and precisely the same thing I am showing in the next diagram, and also I am writing in my expression. This B into h by 2 I have written as area in compression. This B into h by 2 I am writing as area under tension, and then this h by 4 I am expressing as yc, that is distance of centroid of the compression area from neutral axis, and this h by 4 I am expressing as yt, that is distance of area in tension from the plastic neutral axis. A very important result I am establishing. What is ZP? We are trying to understand its physical significance or its meaning. So plastic section modulus is sum of first moment of tension and compression areas about plastic neutral axis. So this is my compression area which I am imagining to be concentrated at its centroid, and if I imagine moment of this area about the plastic neutral axis, it is going to be total area multiplied by this distance, that is h by 4. Similarly, this is my tension area. If I want to find its first moment about the plastic neutral axis, it is going to be the total area multiplied by this distance of the centroid of that area from the plastic neutral axis. So I repeat, plastic section modulus is the sum of first moment of tension area and compression area about plastic neutral axis. a very interesting comparison of plastic hinge and a real physical hinge or internal hinge, which will make our idea about plastic hinge more clear. Essentially, plastic hinge is a section or a small zone where all the fibers have undergone yielding and have developed yield stress sigma y. So I urge you to look at these drawings carefully. If under ultimate point load, I am trying to observe how will be the plastic hinge. So a shape of somewhat like this is formed, which is my plastic zone. And at the same time, if under ultimate uniformly distributed load, if you try to observe how is the plastic hinge formed, so it is formed in somewhat a shape of this kind, which our diagram is showing. Plastic hinge disappears, that is, it is fully recoverable if the structure is unloaded. So if I reduce now this point load or this uniformly distributed load, the plastic hinge will completely vanish. But understand at the same time that does not mean that the material has fully recovered, because material has long since crossed its proportionality limit and elastic limit. So the molecular structure has undergone a drastic change. If you again start loading the material, it will show a different proportionality limit, it will show a different elastic limit. That is what is called as strain hardening. So plastic hinge is recoverable, but that does not mean the specimen has come to its original size and shape. There will be a residual strain present throughout the material. Plastic hinge is characterized by appearance of bending moment. This is extremely important because we are aware that in internal hinge there is ideally no movement. The bending moment at an internal hinge is always zero, whereas the bending moment in plastic hinge is MP, that is plastic moment or plastic moment of resistance, which is the ultimate moment of resistance offered by the section or the zone where the plastic hinge is formed. Ultimate load is independent of sinking of support, fabrication error, pre-stressing tension, temperature changes, etc. So a couple of minutes back, I had commented that finding ultimate load is usually the goal of our plastic analysis. Then this is a very important observation that this ultimate load is independent of sinking of support or fabrication error, pre-stressing tension, etc. etc. A couple of observations about plastic neutral axis. We saw what is plastic hinge. We saw what is plastic moment of resistance. We saw what is plastic zone. A few observations about plastic hinge, comparison with a physical hinge or internal hinge. And now we are seeing this plastic neutral axis. And the question naturally comes to our mind is, does it pass through centroid of the section? Because we know that elastic neutral axis always passes through the centroid of the section. So what about plastic neutral axis? So here I have shown a section in the diagram and I have shown the centroid and I have essentially shown the neutral axis, which is elastic neutral axis passing through the centroid of the section. Very first observation about this section is this is an oval shape which is symmetric about this vertical principal axis, but it is not symmetric about this horizontal axis. And then I have shown for this section the compressive resultant force and the tensile resultant force, and we are aware compression is equal to tension since the beam is not actually loaded. And then I am showing the yield stresses in the compression zone as well as the yield stresses in the tension zone. I have written at a plastic hinge section, each fiber has developed stress equal to yield stress. Since compression is equal to tension, I am writing sigma y into area of compression or area under compression. This is my C, is equal to sigma y into area under tension. This is my T. This is obvious. Stress multiplied by area is the force. Now if I cancel the sigma y term from LHS and RHS, I am getting AC is equal to AT. Area under compression and area under tension have to be equal. Thus, most important observation, plastic neutral axis divides the cross-sectional area into equal halves. Area of compression should be same as area of tension. Nowhere we are saying that plastic neutral axis must pass through centroid. We are just saying that it is such a layer or it is such a line or it is such an axis which divides your total area of the cross section into equal compression area and equal tension area. That is, your area compression and area tension have to be equal. Same thing I have shown in the diagram. I have shown plastic neutral axis here. I have highlighted deliberately the area under compression by a different color. This is area under tension, and now clearly you are seeing in diagram that these two areas might be equal, but plastic neutral axis is not passing through centroid necessarily, or it is not necessarily coinciding with my elastic neutral axis, which is essentially passing through centroid. So I repeat, elastic neutral axis essentially passes through centroid, whereas plastic neutral axis is such an axis which divides the cross-sectional area into two equal halves. Area of compression is equal to area of tension. Then naturally the question again arises that does plastic neutral axis never coincide with elastic neutral axis? Are they never same? Or plastic neutral axis, is it never passing through centroid? So that is not the case, as you are clearly seeing in my drawings that if you have such a cross section which is symmetric about both principal axes, the vertical axis as well as the horizontal axis, then definitely horizontal axis passing through centroid will be your elastic neutral axis as well as plastic neutral axis. Just observe this diagram very carefully. The left side subtitle says section symmetric about vertical principal axis only, where you are having plastic neutral axis and elastic neutral axis as distinct or distant axis. They are different axes. Whereas the diagram on the right side having the subtitle section symmetric about both principal axes is showing that your plastic neutral axis and your elastic neutral axis are coinciding. That is what our observation says. Plastic neutral axis and elastic neutral axis would be same if the section were symmetric about both principal axes, otherwise distant. Extremely important observation. Now we come to shape factor, yet another parameter which is very important in plastic analysis. So I'm just revising a couple of observations that we have already made. We have elastic moment of resistance as sigma y into Ze. Ze is the elastic section modulus, which was I by y max, second moment of area divided by distance of the outermost fiber from neutral axis. And then we have plastic moment of resistance, which is sigma y multiplied by plastic section modulus. What is plastic section modulus? Also we have seen that it is sum of first moment of compression area and tension area about plastic neutral axis. Then what is shape factor? We define shape factor as the ratio of plastic moment of resistance to elastic moment of resistance. Try to understand, we are defining elastic moment of resistance when the yield stress is reached in the outermost fiber, which was in a way end of our elastic analysis, and we are defining plastic moment of resistance when all the fibers of the section have undergone yielding and the section can offer no more stress, no more resistance. So this is in a way ultimate state, and this is elastic limit state. Thus, shape factor is the measure of efficiency of section and indicates the extent to which a section may be stressed beyond elastic limit. I have written here shape factor S is equal to MP upon ME as defined just now, which is sigma y into ZP. Our definition or meaning of plastic moment of resistance divided by sigma y into Ze, which was our definition or meaning of elastic moment of resistance. Obviously sigma y will get cancelled from numerator and denominator, and I get S is equal to Zp upon Ze. It is ratio of plastic section modulus upon elastic section modulus. Thus, shape factor is purely a geometric term. It's a property of shape of the section, whether it is rectangle or a T or I or C, so on and so forth. It is independent of loading and material properties. So nowhere we are considering what is the amount of load. Nowhere we are discussing what is the type of load. Nowhere we are discussing modulus of elasticity or Poisson's ratio. We are simply observing that shape factor is Zp upon Ze, that is completely geometric quantity. Now to understand this shape factor better, I am taking one simple example of this rectangular section. We have already discussed this diagram. I am writing Zp is equal to ACYC plus ATYT. That is equal to compression area is B into H by 2, tension area is B into H by 2, and YC distance and YT distance, as we have already discussed in the diagram, are H by 4 and H by 4 each. So Zp, if you solve this, you will get BH squared by 4. I urge that actually you take paper and pen and try to solve it. You will get plastic section modulus for a rectangular section is BH squared by 4. Elastic section modulus I by Y max for a rectangular section is already known to you as BH squared by 6. I is BD cube by 12, Y max is D by 2, D or H, whichever notation you are using. So if you take I by Y max, it will be BD squared by 6 or BH squared by 6. Now if I take S, shape factor, as Zp upon Ze, which is BH squared by 4 divided by BH squared by 6, which is 1.5. Extremely important observation. Shape factor is what? It is essentially MP upon ME, that is plastic moment of resistance upon elastic moment of resistance, and that I am getting as 1.5 times. This indicates that a rectangular section before failure will absorb bending moment equal to 1.5 times the bending moment at elastic limit. So what we are proving, MP upon ME, which is same as Zp upon Ze in calculation, which is our shape factor, is 1.5. So the bending moment at collapse is 1.5 times bending moment at elastic limit. So this is the importance of our plastic analysis, that after external fiber has yielded, you can further load the structure and it will be capable of absorbing bending moment as much as 1.5 times the bending moment at elastic limit. That's it. Thank you very much for attending this lecture. We discussed several theoretical concepts in this lecture. This was an introduction to plastic analysis, and as we solve numerical examples on plastic analysis, you will understand the significance of these terms, these concepts, and the plastic analysis as a whole more clearly. Thank you so much.